6.3, definite integrals and antiderivatives. So we should have a good idea of what a definite integral is, but let's get some of the properties. And whenever I hear definite integral, I think area under the curve. Now, I've talked about this briefly. It's not just area under the curve. It is what we call a accumulating function. So it can be adding up anything, but this gets me out of a lot of problems. So what's the difference between this and this? And it's a very common question, right, on the AP exam. So this equals 2 because it's from 0 to pi. This equals -2 because it's from pi to 0. So this is something that happens on a regular basis. We have something where the bigger one is on the bottom instead of on the top. We flip them around and slap a negative. Do that all the time. We get this once in a blue moon when it goes from A to A. So we have basically no area under the curve. We get 0. I use this technique a fair amount when I'm integrating. I have a K and it's stuffed inside. I throw it out front just to get it out of the way. Throw the negative out front, same thing. Sum and difference, you can break them into 2. We do this all the time. It's not a big deal. And if they go from A to B and B to C, you can break them into A to C. We actually turn this one around a fair amount. This one at the bottom is, pardon my expression, stupid, but it's basically saying, hey, we've got a curve on here. Well, if we know where the max is and go from A to B, then the area in the box is bigger than the area in the blue. That's all it says. All right. So, yeah, don't worry about it. It's kind of a dumb question. Yeah, anyway, that one also never pops up. Never gonna see that one. So let's finish up here with this concept that if I graph something, and here's g of x, some curve, and here's f of x, some curve. If f of x is always greater than, it could be equal, this could touch here, then the area is going to be greater. Duh. If f of x is greater than 0, then the area is going to be greater than 0. Duh. None of those really help. The ones at the beginning on the other side really help. So let's see what's going on here. This is actually not an uncommon AP problem. Really not a big deal. Nothing that I would consider complicated. It says, hey, the integral from 4 to 1. And your immediate instinct is, I should probably go 1 to 4. Oh, well, 1 to 4 is -2. So the integral from 1 to 4 of f of x dx equals -2. So when I flip it, it becomes negative, which is 2. All right, well, what about from -1 to 4? And I said this is what this usually is, -1 to 1, 1 to 4. So that equals the integral from -1 to 1. And be careful here, because sometimes, yeah, we get an h of x, f, h, and kind of gets lost when you're trying to sort these out. Plus integral from 1 to 4, f of x dx equals 5 plus -2 is 3. And then down here, we're going to break them apart. We know -1 to 1, we know -1 to 1. So we're going to go with 2 times integral from -1 to 1 f of x dx plus 3 times integral -1 to 1 h of x dx. And we're going to get 2 times 5, running out of space a little bit here, plus 3 times 7, 31. Now the integral from 0 to 1, you go up here, I don't see any zeros. So, okay, well, what about the integral of -2 to 2 for h of x? Well, I can't just hit it times 2, which a lot of people think they can. Well, the integral from -1 to 4 of f of x, Okay, I can do that. I've already actually done it here. And well, I can't do it for h of x, so cannot be determined. And I put these up here. They're not going to do cannot be determined on the AP exam, but it's kind of nice to be aware that you have to look very carefully at your problems and understand what's actually going on, not just slap something at it and pray that it'll work out for you. We're going to get into the real integrals soon, but I still have a few more examples here, just to be clear. So that this value is less than 3/2. Okay, well, cosine maxes out at 0. It's 1, so that's the square root of 2. And then it mins out at, well, we're going to stay above the x-axis, so it mins out at pi over 2. So that's 0 to 1, it says. Pi over 2 is 1.57. Okay, so it's just going to max out. It's a square root. Well, I don't know what that is, but I do know when I plug in 0, it starts at square root of 2 and becomes less. All right, so we're going out here to 1. Whatever is going on in here, I have no idea what's going on in here, and I purposely make a crappy curve. The outer edge will be greater than that inner one. So we would say square root of 2 times 1 is root 2, which is 1.414, which is less than 3/2. All right, so that's just an example. You would never do that on a test. They're just trying to show you how it's area, and yeah. I will say remembering its area under the curve helps me in a lot of problems when I get lost. So mean value theorem for derivatives. Yeah. Some funky curve. Interval from A to B. Parallel lines. F prime of some C. And then slope. We would say F prime of C is going to equal the slope at some C, something like that. It doesn't really matter. Why do we find it? No idea. My answer is the math teacher thing. They find it so they can write problems about it. All right, and they say it comes in helpful when we do increasing and decreasing. Yeah, I'm not really a believer in that, so we'll just say it was used for proving other things. All right, now can we find the average of a continuous area? Let's slow that one down a second. Average these 4 values. Well, I would just add up the y value, divide by 4. Well, what if there's more of them? What if there's even more of them? What if there's an infinite number of them? How do we add up this area? We use an integral. We want the average value. So we look at this and we say, it's usually around about there. That's the average value. On a table with bounciness to it, it's very upsetting. And how do we find that average value? Right down here. Now, let's back up a step. Now, we can always add all these up. Yeah, sometimes we can just think about discrete things. For the last year, we have been building stuff, and every hour we average the number of cans we make at our can factory. Who knows? I'm making things up. We can actually add them up, but it'd be a lot easier to do an integral because that's 24 hours a day, 365 days a year. Punching every one of them in takes forever. Well, we have a graph that it increases during the day and decreases at night when we have a later shift. We can use this little technique. So we say just find the interval A to B and then divide by the interval. All right. Really, I couldn't find a better word to use than that. No, I couldn't. Now here's the problem. I come rolling across a problem. My brain is barely able to keep it together with all this calculus. And I see average. I go, ooh, average, AROC. I remember that. Average rate of change. Here we go. When they ask for the average value, not asking for a derivative, they're asking for an integral. So I'm going to use this weird little notation up here. I never really noticed that before. The average F, sure, whatever. 1 over 3 minus 0, integral 0 to 3, 4 minus x squared dx equals 1/3 4x minus x to the third over 3, 0 to 3 equals 1/3. I can toss a 0 out. You can't always toss the bottom value out, but 0 is going to get rid of things. 12 minus 3 times 3 is 9 times 3 is 27 over 3. 12 minus 9, 3 over 3, 1. And then it says, does the actual value take, does F take on the value at some point? It kind of has to, if you think about it. Go up to this curve. There's no way you can get an average value that doesn't come. I mean, if it's a constantly increasing function, it's going to hit somewhere. If it's constantly decreases, you know, so I think it's got to hit. So when does f of x equal 1? So we would say 4 minus x squared equals 1. X squared equals 3. X equals plus or minus square root of 3. Which one's in the interval? Just the positive one. Interesting, huh? Yeah, that's it. That's it. Notice the graph of this actually goes below ground, below the x-axis. That was funny. At 2 here, so we're at 0. The average value adds up the positive and the negative aspects of it. And the average value is 1. So that would be, starts up here at 0.4. The average value would be down here at 1. Sure, you say so. I love graphing after I'm done with a problem, so I can figure out if I did the thing right or wrong, but this is not one of those cases. I'm not really sure what that means, but you know, if that's an average of 1, I don't know how I would check that and say, oh, that makes sense. It's kind of weird. So anyway, this is the mean value theorem. F is continuous, some point on there. There's going to be a value. We just found it. The value was at x equals root 3. The total value here was 1, but it happened at root 3. Yeah, that's it. So the hard part here is just knowing what they're asking for. Look for the word average. And let me rephrase that. The words average value. Now that's not accurate. They might ask it in a slightly different way, but I cannot think of what they would do off the top of my head. So fun times, more math for the sake of math kind of thing. So now we're going to try and put these two together. This is what the next lesson is. How do you put these two together? The derivative of an integral, they cancel out and just get the functions. You say, oh, they're inverse functions. No, inverse functions would get us what? Inverse would get us x. Got a fly bugging me here. What would we call these? I don't really know. Opposite functions. Invert? No, it's not inverse. It's a good question. But they cancel each other out. Multiplicative inverse? Cancel each other? No, they get you 1. I don't know. It's kind of weird. So this I talked about. This means antiderivative. Okay, so how do we use this? Well, derivative of what is sine? This is where we're going with this, and this is where you can't use your calculator on the test at the end of this unit. Well, it's negative cosine of x, because derivative of cosine is negative sine. Negatives cancel out. Build a little wall. And now we go negative cosine of pi. At this point, you're like, well, we can throw out the 0 because, careful, minus negative cosine of 0. That's negative, if I'm not mistaken, negative 1 plus 1 is 2. Antiderivative of this is x to the 4th over 4. See ya. Build the wall. Can't throw out the bottom one. Equals 2 to the 4th minus negative 2 to the 4th equals 0. How can that be 0? That makes no sense. I told you earlier, I like to graph things to make sense of things. I graphed 4x to the 3rd from negative 2 to 2. It does something like that. So this area cancel out. It'll make sense. In case you're wondering, most people, just doing what you tell me to do. Okay, let's do this one graphically first. 4 from 0 to 5. 20. Let's do it right. 4x, build the wall, 0 to 5. 4 times 5 minus 4 times 0 equals 20. Cool. And then e to the 4x. So a lot of people get bothered when I do this quickly. A, I'm cheating. I have it sitting next to me. And B, just take the derivative of the top. E to the 4x times 4. 4's cancel. I'm back here. Works. It takes some practice, but yeah, you should be able to do it. E to the 4th over 4 minus e to the 0 over 4 equals 1/4 e to the 4th minus 1. I will see this kind of problem often, and I will see sometimes written like this, sometimes with 4 on the bottom, sometimes separate terms. Doesn't really matter. Whatever gets it done. All right, that's good stuff. Now we're getting into it. So good luck and happy mathing.